In this problem, we're asked to determine the normal force, the shear force, and the moment at point C in the beam. This is an internal forces or internal loading or loadings type problem, and as I said in the lecture, we use the term internal forces and internal loadings interchangeably. And for the 2D case, the internal forces or internal loading is composed of a normal force, a shear force, and a moment or bending moment about point C. And for the 3D case, we add a fourth component known as the torsional or twisting moment. So this is a 2D case, and we're going to start the problem by taking a cut through the point of interest. Which is at C, and then looking at the segment of the beam to the left of the cut and the right of the cut and determine which side we want to work with. And this is very similar to what we did with the method of sections for simple truss. We want to pick the side that of the cut that we're most comfortable working with, and usually that's going to be the side that has the least amount of things going on. In other words, if we look at the left side of the cut, our free body diagram of that segment of the beam is going to include the distributed load as well as an unknown reaction at A. If we look at the right side of the cut, the free body diagram of that segment would just involve the unknown reaction at B. So this one's pretty straightforward. It's pretty obvious we're going to work with the right side of the cut. So I will write that down. Working with segment to the right of the cut. Okay. Now, before I draw that free body diagram of the segment, I know that I need to find the reaction at B. So the first thing I'm going to do is solve for the reaction at B by drawing a free body diagram of the entire beam. And I am going to take a shortcut. I'm not going to redraw that beam and subject the viewer to a bunch of squiggly lines. So I'm going to cheat a little bit and use the original figure for my free body diagram. So I'm going to have a reaction force at A, since that's a roller that the beam is resting on. I'm going to have a reaction force at B in the vertical direction, and I'll show the reaction. I'll call that B sub y, A sub y. We can show the x component of the horizontal component of reaction at B. Now, at this point, we should be able to see that that's going to be 0, and in a lot of these beam problems, everything's just in the acting in the vertical direction. But we'll put it there and write the equation of equilibrium in the x direction to show that. And then for the distributed load of 3 kips per foot, rectangular distribution, I'm going to show a resultant force, an equivalent force of 3 times 6 is 18 kips. And that is acting at 3 feet to the left of A. It acts through the centroid of that rectangular area, which is 6 feet wide. Okay. Now I'm going to apply the equations of equilibrium to the free body diagram of the entire beam, and I'll get B sub x out of the way first. So the sum of the forces in the x direction equals 0, and I can see that the only thing I have going in the x direction is B sub x, so therefore B sub x is 0. And I can solve for B sub y directly by summing moments about point A so sum of the moments about A and that's going to include 2 moments, B sub y times the 9 feet that it's away from A, and then the 18 kips acting at 3 feet. Okay, and we do that math, and B sub y is equal to -6 kips. And that makes sense. B sub y is pulling the right end of the beam down. It's the A is acting like a fulcrum, and that load on to the left of A is trying to rotate the beam counterclockwise. So that makes sense. Now I'm going to draw the free body diagram of segment on right side of the cut. Okay. Okay. So I'll show B sub y, and I know that that acts in the negative direction, or the down, and it's 6 kips. And then at the cut, I'm going to use the convention for the unknowns that we established in the lecture. I'm going to show a normal force that in the direction such that it's pulling away from the cut or trying to cause tension. I'll call that N sub C. I'm going to show a shear force, unknown shear force, that tends to rotate the beam segment clockwise. And I'm going to show a bending moment, and I'll put it out here for that tries to bend the beam in a so the beam would be concave upward fashion. In other words, it's trying to make the beam bend like this, okay, concave upward. Okay, so again, this is the cut here. I have a 4.5 foot distance from the cut to the right end of the beam, and now I can apply the equations of equilibrium to this free body diagram. I have 3 unknowns, V sub c, N sub c, and M sub c, and 3 equations, so I should be able to get there. Okay. So let's sum forces in the x direction. We should be able to see that n sub c is equal to 0. In the y direction, should be able to see that I have v sub c minus 6, so therefore v sub c equals 6 kips. And then in my moment equation, I'm going to sum moments about the cut. So assuming counterclockwise is positive, then m sub c is going to be negative, and the 6 kip force is also going to be negative, and it'll be 6, the moment will be 6 times 4.5. So therefore, m sub c equals a negative 27 kip feet, or 27 kip feet counterclockwise.